Capacitors, this is 6.6. This is where I get a little bit fuzzy, I have to admit. I added this material and I'm not 100% certain about how this all works together, but that's okay. Capacitors are an important part of circuits. These are things like resistors or light bulbs or batteries. They're parts of a circuit, but their job's a bit different. They store up charge temporarily. They work by having two parallel plates of conductive materials that are oppositely charged, one positively charged and one negatively charged, but there's a gap in between. And so the charge cannot cross through that gap until it builds up enough potential energy that it can suddenly spark across. And so it creates like a timer almost, because it builds up the energy, sparks, builds up the energy, sparks, builds up the energy, sparks, and it creates like a rhythm or a heartbeat or whatever, however you want to think of it, in the current in the circuit. And so in our circuit diagrams, we're going to see these as two parallel lines that are identical in length. So it's similar to the battery symbol, but a battery has one long line and one short line. These the two lines are both the same length. And they can be used as temporary batteries because they store charge. They're used to make lights flash. They're also used to smooth out the power, because if you get that flash going fast enough, it's like a continuous level of power instead of having like smoother up and down swells of power. It's trying to create a smoother power source for really delicate equipment. Okay, so how much potential difference it can store up, how much voltage it can store up, is called the capacitance. Well, okay, the ratio of the charge to the voltage. And capacitance is measured in farads, capital F, where the capacitance is equal to the charge divided by the voltage. Charge is in coulombs. We talked about electrical charge already, about sort of like the number of electrons that are moving across, except it's more about how much positive or negative charge they have. And divided by voltage, the change in the potential energy. Yeah, so that gives us our capacitance. However, a single farad is usually too large. That would be 1 coulomb per volt. Instead, it's usually microfarads, which is mu f down here, or nanofarads, nf, instead. Mu f is equivalent to 1.0 times 10 to the negative 6, and nf is 1.0 times 10 to the negative 9th, to put that into perspective. And so our capacitance values tend to be really, really small. So energy is being stored in our capacitors. This energy takes the form of the work done by sparking across the gap, how much energy is in those sparks. So energy is measured in joules. We're going to give it the letter U in our formulas here. And then we still have Q and C and V for charge and capacitance and voltage. And so we have three different formulas, where U can equal 1/2 of Q times the voltage, or U can equal 1/2 of Q squared divided by C, or U equals 1/2 of C times V squared. It depends on what type of information you're given in the problem. Let's look at an example. A capacitor is fully charged with a 10-volt battery, so we have a voltage, and has 20 millijoules of energy. So that's U, millijoules. Milli is 1/1000th, so 20 millijoules is the equivalent to 0.02 joules. Like a millimeter is 1,000th of a meter. Centimeter is 100th. You guys know these. Okay. So we have V and U are being asked to find what is the charge. So what is Q? So we need a formula of V, U, and Q. So V, U, and Q, that's this first one. We're going to rearrange it to solve it for Q. So U equals 1/2 Q times V. So Q, we'll divide out the V. So 1/2 of Q is U divided by V, and then times 2. So 2U over V. 2 times 0.02 divided by 10, 0.004 coulombs. C. Okay. We can also have more than one capacitor in a circuit. When we're trying to find the sum for our capacitors, they work similar to the resistors in that the formulas are the same, they just switch places. If it's in series, then we do the inverses. 1 over the total capacitance is 1 over C1 plus 1 over C2 plus 1 over C3, etc. And if they're in parallel, then it's just a simple sum, C1 plus C2 plus C3. So another example, what would be the total capacitance for this complex circuit? Well, these aren't all in series. It kind of looks like they might be because it's all in the same square, but you can see the current enters on this side and it's going to come out on this side. And so this half of it is parallel to this half of it. These two are in series with one another. So we're going to solve for this part first in series and then just add it to this one that it's parallel to. So 1 over c on the top is going to be 1 over 500 plus 1 over 100. We can just leave it as microfarads. It's the same as long as they're all the same unit, so it works fine. So 1 over 500 plus 1 over 100 is 6 over 500, and then we flip it right side up. 500 divided by 6 is 83.33 microfarads. And then since it's in parallel, so bottom one, the rules that we just added. So 83.33 plus 50 is 133.33 microfarads. And that's the answer. Alright, so that sort of gives you an idea. You are going to be doing both these types of equations, picking the right formula from these 3 formulas, or looking at a circuit diagram and calculating total capacitance. Again, remember we're going to round all our answers to 2 decimal places, and then you don't have to put the units in your answers on the worksheets because it doesn't do a good job reading those. So anyway, hopefully that's enough, and you can contact me or get on the science chat room this afternoon or however you want to. I know we've been struggling a bit with Google Forms. It is not like math. It's very literal. Or maybe I'm not using it right. I don't know, but I'm still working with it, and I hope it's not too frustrating for you guys. Have a great day. Don't forget we have a quiz tomorrow, and then weekend. All right.